There's a problem about geothermal energy, and it says a power plant taps steam superheated by geothermal energy to 505 kelvins, the temperature of the hot reservoir, and uses the steam to do work in turning the turbine of an electric generator. The steam is then converted back into water in a condenser at 323 kelvins, the temperature of the cold reservoir, after which the water is pumped back down into the earth where it is heated again. The output power work per unit time of the plant is 84,000 kilowatts. Determine A, the maximum efficiency at which this plant can operate, and B, the minimum amount of rejected heat that must be removed from the condenser every 24 hours. This here is a schematic of how such a geothermal energy production plant can look like. Obviously I got this from a website from Iceland, which is the front runner in the world for geothermal energy, simply because that's a volcanic island, and as you can see here, the heat comes up, and that then drives the turbines, and then it's being pumped down now as cold water again, and then it comes through here and again superheated and comes back through here. So it's kind of cycle here. So here we have the hot reservoir and the high temperature, and here we have the cold reservoir and the cold temperature. The schematic from the book is this one here. So here we have the hot reservoir, heat goes into the engine, the turbines, work comes out in this case as electrical energy, and then the excess heat goes back into the cold reservoir, and yeah, as this one here shows, then it starts over again. Okay, let's see what we have given in the problem. And that is, we have the two temperatures given, so the high temperature as well as the cold temperature. So TH is given and TC is given. And in a previous problem, I wrote these as TI and TF according to what they give us, the kinds of equations that they give us in the book, because I realize it as such initial temperature, final temperature. Here I realize it as that we're talking about cold temperature, hot temperature, and so I might as well label them like that. We're supposed to figure out what the efficiency is, E. Then what else we have given is the output power of the plant is 84,000 kilowatts. So we have given, capital P for power. And we're supposed to figure out what the rejected heat is that must be removed, and that would be the QC. So there's a question mark there. And then we have one more given, and that is must be removed from the condenser every 24 hours. So we also have time given, and we'll see where that one plays into. Okay, the very first part, A, is really straightforward. The title of the section is Carnot's principle and the Carnot energy in engine. So in this case here for this problem, we have to assume that indeed we're dealing with a Carnot engine, and basically why the book keeps doing that with the Carnot engine, because the equation for that is really simple and can be written as E equals 1 minus TC over TH. So here all we have to do is plug in the numbers, and you come up either as a decimal or as a percentage. And so that would be 1 minus 323 divided by 505. That gives us the decimal, and then move the decimal point twice over, and we come up with the percentage. Of course, our temperatures both have to be in kelvins. They already do that in that problem, but be aware if you get a problem that gives a temperature in Celsius, you have to convert that first, because you need to have absolute temperatures in the metric system and kelvins in the American system in Rankins. By the way, there's also the equation for the efficiency of 1 minus QC divided by QH. Now that equation is the same for, whoops, I don't know why that jumped, is the same for all engines. That's always applicable, and for the Cutnell engine itself, it becomes this easy, simple expression here, 1 minus TC over TH. That's not the case for other engines. For example, for the diesel engine, this is the formula. This one right here looks pretty bad. In fact, the alpha here is what is called the cutoff ratio, so a ratio of the two volumes. You go through the PV diagram and you have 1, 2, 3, 4 points, and each one of them is a certain volume. And so here you have a certain ratio of the volumes, and then the R is the compression ratio, V1 over V2. Of course, they depend on the temperatures as well, and of course the gamma is given as the adiabatic index. And yeah, the equation looks quite bad, and for a internal combustion engine, the Otto engine, it looks just as bad. And that's why they tell us, just use it an approximation as being a Cutnell engine, even though that's not true, but at least the equation is relatively simple. Okay, for part B, how can we figure out what the heat is that needs to be rejected from the condenser? Well, the one equation that we have actually we have two equations. The one that I already wrote down here, but we don't have QH. We are supposed to figure out what the heat is that is being rejected, but we don't have the amount of heat that comes in. So, if we use that, we'd have two variables. The other equation is this one here, the conservation of energy for a heat engine. QH equals work minus plus QC. And again, we have two unknowns, QC and QH. The W is given. That was the 84,000 joules. Yeah. Oh, I'm sorry, 84,000 kilowatts, which is 84,000 kilojoules per second. Again, here we have two variables though, QC and QH. However, there is a second equation that we can apply now, which is that the efficiency is work divided by QH. So QH is the same as work divided by efficiency. So when I substitute that in here, work divided by efficiency, which I, by the way, just calculated, then I come up with this one, work plus QC. Okay, and then the only unknown that I have is QC, so it's going to be QC equals work divided by that efficiency minus the work. And then I take back what I said a moment ago, work is not 84,000 kilojoules per second. Work has to be in joules, but that's where the time comes in. The work that is given or that is being calculated or can be calculated by power, that's the power that's given in the problem, 84,000 kilowatts. Power times the time, that is also given as 24 hours, but that has to be converted into into seconds. And so this one is going to be 84 million watts times 24 hours times 3,600 seconds. Divide by that efficiency that was calculated up here, out of the picture at this point. So calculated up here, and then divide by that efficiency minus again the 84 million watts times 24 hours times 3,600 seconds. Overall, for the rejected heat, you come up with a pretty large number, and that will be then in joules, 10 to the somewhere around 10 to the 13 or so.